All right, let's take a look at the graph. Can I erase this? This problem is in the book. I'm not just like, let me cook up the worst problem I can think of. This problem is in the textbook. And it's not one of the hard ones in the back of the section. You know what I'm talking about? Those ones that they put in the back. This is actually number 20 out of the next section. In the next section, you're asked to graph the entire function. So you have to do all this anyway. Okay, so let's take a look at it. Desmos, our friend, square root x squared plus x minus x. There it is. So do we have a decent graph? Do we have a decent idea of what was happening? Our domain was from -1 to 0, right? To the left of -1, we are decreasing. Is that what we said would happen? It was decreasing. This is a local minimum. It is the lowest point. At -1, it was up at 1, right? That's a local minimum because it's the lowest point nearby. But remember, you're not allowed to look in here. So near this side, it's the lowest point. And also, can you kind of tell that this is concave down? Can you kind of tell it looks like a frown? Okay, and then we jump to the other side. It's always, was it increasing? It was increasing, right? It was up arrow. And it's concave down. Second derivative was negative. And then we have a local minimum there at 0, and it was 0. So our information matches the graph, doesn't it? All right. All right. What do y'all think?
This is still 2.3, right?
4.3. Actually, we're doing concepts in 4.3, but I'm using problems from 4.4. Because I've already done all the homework videos and stuff. I don't want to redo problems. Let's take a look at e to the x over x squared. Same instructions. So we'll need both derivatives, right? So let's go ahead and get those. First derivative, oh, domain, sorry, we should talk about domain. What's the domain of this function? Everything except 0. Okay, so I'm just going to put, instead of telling you what x can be, I'm just going to tell you what x can't be. X can't be 0. So when we draw our picture, we got to make sure 0 is not in play, all right? So our first derivative is going to be e to the x times x squared minus 2x e to the x all over x to the 4th. So that was my quotient rule, wasn't it? Derivative of the top times the bottom minus derivative of the bottom times the top. And I will clean this up a little bit. Notice that the numerator has a GCF, doesn't it? Greatest common factor? Of what? What can I pull out? An e to the x and an x, right? So let me pull an x e to the x out of the top, and I'll be left with x minus 2. Right, that's what would happen if I pull an e to the x e to the x out of the top. But on the bottom, I have x to the 4th. And so I wanted to do that because I wanted you to see that that would become a 3 and that x is gone, right? So I guess a nice clean version of our derivative is this. Okay, that's our first derivative. Now what? Second derivative. So our second derivative, uh-oh. How do we get the second derivative here? We have to do quotient rule, right? But to do the quotient rule, we actually have a product in the top, don't we? Now, I'm going to avoid that. I'm going to slightly avoid the product rule. I'm just going to do this. No, that's still not going to avoid it. I'm still going to get a product. I'll live with it. Okay. So let me draw what's going to happen here. I'm going to have the bottom is going to be x to the 6th, right? Because I'm going to have derivative of top times the bottom minus derivative of bottom times the top, all over the bottom squared. So there's the bottom squared, right? Okay. What is the derivative of the top? That's a product rule, right? So it would be derivative of this times this plus derivative of this times this. Yes. Let's do that real quick. Derivative of this times that, x minus 2, plus derivative of that, 1 times that. All right. That's the derivative of the top. The derivative of the top times the bottom minus derivative of the bottom. Yes, x cubed. Sorry, I've got ahead of x cubed. I'm working on this. Derivative of the top times the bottom minus derivative of the bottom times the top, which is that big ugly thing. Oh boy. Yeah, that's it. We will have to set that equal to 0 at some point. Yeah, there's some things we can do here. Let's clean this up before we finish and start doing the up-down stuff. On these two right here, what do they both have in common? E to the x. I'm pull that e to the x out. And what would be left inside that parenthesis when I pull e to the x out here and e to the x out here? X minus 2 plus 1, which is really x minus 1. So that's x minus 1 there. And then I still have the x cubed being multiplied. And then over there we have minus 3x squared e to the x times x minus 2, and then all over x to the 6th. Now, looking at this big, ugly numerator, I have two pieces. I have this piece and I have this piece. There's a GCF in those. I can pull an e to the x out of both, and I can pull an x squared out of both. So I'm going to put x squared, e to the x out here, and then what would be left if I pulled the e to the x out and the x squared from here? I'll be left with this and an x. So x times an x minus 1. And then if I pull an x squared out and an e to the x here, I'll be left with a minus 3 and then this. All over x to the 6th. Two of these factors cancel. Remember I said we could do the raw derivatives, but at some point you're going to have to be able to manipulate the derivatives? That's today. Okay, so I'm gonna clean up the inside of this now. I want to know what all that is. So I'm just going to go here, here. So x squared minus x, and then what? Minus 3x plus 6. So all that together is going to be x squared minus 4x plus 6. And that's all over x to the 4th. That is a pretty cleaned up second derivative now. Right? Okay. So we have our first and second derivatives. Any questions on the algebra here? Okay, so I'm gonna rewrite our first and second derivatives right here. I'll write their cleaned up versions. So my first derivative is this one, e to the x, x minus 2 over x cubed. And then my second derivative is e to the x times the quadratic x squared minus 4x plus 6, and then all of that over x to the 4th. And now I get to work with these, right? So let's determine where our function is going up and down. So take my derivative, set it to 0. So I take e to the x times x minus 2 over x cubed, set it to 0. And that means I only have to concern myself with the top, right? So this means that only e to the x times x minus 2 has to be 0. And can e to the x ever be 0? No, it's the exponential function, right? It looks like this. And it never hits 0. So that can never be 0. So the only thing that could ever get me 0 is this. So I have one solution here. X is 2. Right? Now, what about anywhere where we're undefined or where it doesn't exist? At 0, right? Remember though, 0 is not in our domain. Do you agree? Okay. So now we don't have to worry about this, but we do have to worry about it. Let me draw a number line. What should I put on this number line? Yes? What was my critical number? What did I get from this? 2. So 2 definitely goes here, right? It's going to break up my number line like that. But 0 also needs to go here. Not because of this, but because 0 is not a point in my domain, right? So this point right here, my function is undefined here. I'm going to do this in a different color. Looks the same, I know, but that's purple. Okay, there's something happening over here, something here and something here. We're going to have to check each region. Because this is splitting up my domain, I need to check both sides of it. So I'm going to check here, here, and here. And those test points are -1, 1, and 3, let's say. And those go into what? Those get plugged in. The first derivative. So we could plug it in here. I think it'll be easy to do. We could probably do it just visually. E to any power is positive, right? Is positive. So this is a positive number no matter what. What happens if I plug -1 in here? Get -3. So I have a positive number times -3 over what's -1 cubed. -1. So you have a negative on top, negative on bottom. It's going to be positive, which means my original function here is going up, right? Okay, now let's plug 1 in. What happens if you get 1 in here? Positive, negative, positive. So negative on top, positive on bottom. Negative, which means we are going down. And then finally, if we plug in 3, it'll be positive. All right. I see a lot of drifting minds here. So change my perspective of me thinking you're not paying attention. Do we have any local max or mins? Where?
0, 1, 2, 2.
Okay. So what do y'all think?
No,
No, that's not right.
0 can't be included.
So I'm trying to make a point. I see people just kind of, you know, if you're that comfortable, then just go, you know. But if you're here to learn something, pay attention. All right? Because there's little subtleties in here that if you're not paying attention, that's why you're not going to pass the next test. It's the subtleties of this. You can't sit here and look at it and be like, oh yeah, I could do that. Yeah, I get it. I know what he's doing. This. No. So if you think there's a local maximum at 0, you are wrong. The picture looks like there is. But what's wrong? What's the issue here? Zero is not in the domain of the function. To have a maximum, you have to have up and down. Yes, I agree, but you have to be defined there. You have to have, the function has to have a point there, or else that can't possibly be a maximum. And 0 can't go into the original function. All right? Now, do we have a local minimum? Yes. We go down, then up, and 2 is in the domain. So we know we have a point. When we plug 2 into that function, we have a point that will be the lowest point. Okay? These are those little things that on a test, yes, you may get this all right, but if you tell me I have a max at 0, to me that's fundamentally you don't understand something. Okay? All right. So let's kind of put it all together into a conclusion for where it's going up and down. Okay? So let's write. I hate to call people out, but it's distracting to me when people are sleeping or not paying attention. Okay, where is my function going up? Negative infinity to 0, right? Who was it that asked me about the interval at the end of class? That was you, right? Okay. See what I'm talking about? I said, oh, like, let's always use open intervals. It'll keep us safe. This is a perfect example that 0 is not in our domain. So by leaving it open, I'm not going to get in trouble. If you put it closed here, you're wrong because 0 is not in the domain. Does that kind of help you see why it's safer?
But I also have a question about the maximum, because if you're going to do the open bracket, then it wouldn't touch 0. So wouldn't that also be a maximum, local maximum? If you're not?
Let's talk about it when we get to it. Yeah, that's a good question. All right, so now that's where it's going up. Anywhere else? 2 to infinity? And then where is it going down? From 0 to 2. All right, so that's all good, right? Where it's going up, where it's going down. Now, any local maximums? So this is kind of your question. Do we have a local maximum? You're saying no. Why? Do you have a justification? You're right, but why?
Because it's going to just, well, I guess you could because it's going to stop.
So if I tell you right now that the function is undefined here, right? If it's undefined, then it's going up, then we're probably going to have an asymptote here. Okay, it means it's going to keep on going, right? Let's say it didn't. Let's say that it went like this, and let's say there's an open hole here. So what we're saying is, what if the limit, as we approach from the left, what if it was approaching something? I'm just going to make it up. Let's say this was 4 here. Could we say that the local max was 4? No, because it never reaches 4, does it? Like, it gets closer and closer to 4. How close can you get to 4? As close as you want, right? And if you think you're as close as you can get, I can always find something closer. So there still is not a maximum value. Does that help? So it's either a vertical asymptote or it's this. Either way, because it's undefined there is none. There is no local max. Now, do we have a local minimum? Yes, there we do. There we do. Because down then up, right? And it's defined here. So we have a local minimum at 2. So we plug 2 into the original function. If I plug 2 in there, I get e squared over 4. Whatever that number is, that's a local minimum. All right. Second derivative time. These problems are long, huh? Okay, so the second derivative I need to set that equal to 0. So the second derivative equal to 0 means I'm setting e to the x squared minus 4x plus 6 all over x to the 4th. Set that to 0. I only have to worry about the top, right? I only have to worry about when the top is 0. But why am I leaving off the e to the x? Because it's never 0, right? So this is really the only thing that I need to worry about. So is that ever 0? Well, that's a quadratic, right? So you can use a quadratic formula. I'm going to do a real quick check to see if this has real zeros or not by just looking at the b squared minus 4ac part of the quadratic formula. If this turns out to be negative, I know that I don't have any real answers, right? Let's just check it real quick. B squared would be what? 16, and then minus 4 times A, which is 1 times C, which is 6, and that means I get 16 minus 24, and that's negative, which means this has no real solutions, right? Which means my second derivative is never 0. First derivative was 0, right? There was a place where it was 0 at 2. Second derivative is never 0. So what I'm going to do now is draw a number line. Am I going to put anything on that number line? 0, because it's that domain split. So this is still an important point. And I'm going to pick 2 test points, here and here. And where am I going to plug those in? Second derivative. So let's plug it in. Let's do 1 because I think 1 will be easier. E to the first, that's positive. 1 to the fourth, that's positive. So really, all that's determining whether or not it's positive or negative is here. So what happens if I put 1 here, 1 here? Get a positive? Yeah. So that means this thing is concave up over here, right? What if we plug in a negative 1 into that? What's e to the negative 1? Still positive, right? Because e to anything is always positive. Negative 1 to the fourth, still positive. So these are both positive. If I plug in negative 1 here, I get 1, right? Negative 1 here, I get plus 4, and plus 6, I get positive again, right? No inflection. What if this had been, though, down then up? Would I have an inflection at 0?
No.
You wouldn't, because the point has to be in your domain. Has to be in the domain, just like the local max and min. All right. So where's this thing? Where is my function concave up? F is concave up on negative infinity to 0, union 0 to infinity. So you have to jump over 0 because it's not in your domain. And then where is it concave down? Never, right? How do we say never in interval notation? Does anyone know how to say never in interval notation? Cross thing? You all seen that? No? So military people might say that that's a 0. In the military, they use that for 0. But in mathematics, that's called the empty set. It's the set of nothing. So they're completely different meanings. Think of it this way. These intervals are like baskets, okay? And so when you look at that interval, you're saying inside that basket is every negative number, right? Forever. And then all the way up to 0, but not including 0. That's what's in that basket. This basket is everything, positive, right? This says I have an empty basket. The basket has nothing in it. It's the empty set. So it's the set of nothing. Make sense? All right, no inflection points, right? Let's look at the graph. E to the x over x squared. Did we have decrease, increase, decrease? I don't remember us doing that. Did we? Yeah, oh yeah, we had a local minimum. That's right. I just forgot. So look, to the left of 0, were we increasing? Go back to the first derivative. Were we increasing? Yeah, and you can tell it's increasing, right? But I have no local max or anything. Then on the other side, I was decreasing until I got to 2, and then from 2 on, I was increasing. There was my local minimum, right? Concave up, concave up. Yeah, so how many problems did we do today? 3? Including I did the second part of the quiz problem, right? And then I did 2 examples. And it took us the whole class. So your homework, which I highly recommend you do, I'm going to see here what the homework solution videos look like. They're long. What is this for 4-3? So for 4-3, oh, there's more. There's 3 parts. So the video solutions for 4-3 took me a little over 2 hours to do, right? So that should take you like 8 hours to do. I mean, really, because I expect that it'll take you 4 to 5 times as long to do a problem. So your test that is scheduled for May whatever it is, let's see, May 2nd, there's 2 more sections before that test. 4.4, which is curve sketching, which is where we put everything together. I give you a function, I ask you to sketch it. All right? That doesn't mean you get your graphing calculator out and draw me what your graphing calculator gives you. It means you go through this entire process, and in the next class we'll summarize like, okay, how do we do a sketch? And then after that, there's the optimization word problems. So it is possible that your next test could potentially have 2 or 3 problems on it, and that's it. What? Yeah. It could be that. I mean, because there's just no way I can expect you to do the amount of work required here. So that means you have to be like, you have to know how to do this. All right. I guess that's what I'm getting at. Don't skip this homework. If you're sitting here in class and you're watching me going, yeah, I could do that on my own. Yeah, I get it. I don't need. Don't do that, because you got to do this homework. Yes. I may do a take-home portion, but there will be an in-class part. Yeah, that will take the whole class. How do you all feel about me moving the test to the 25th of this month? Yeah, of this month. So let's see when that lands. When is that? Oh, that's next Thursday. So what would happen is we would come in on Thursday this week. We would do 4-4, more sketching problems. Then we would come in on Tuesday of next week and we would do more sketching and wrap up anything. And then that next Thursday you would have the test. The other option is to not do that and then do the word problems also and then have those also on the test. Why don't y'all think about it? Think about it. Why don't you do the homework for this so you can appreciate the amount of work involved and then decide if you want that and word problems on that test. But let's make a decision about it next class. We'll do a vote, all right?
I won't be here the 25th, so can I take it before if it comes to the vote that day?
We can work something out since I'm changing the date. That's fine.
Because that's
All right.
what I told you about, like, at the beginning of
Yeah, we can work. Let me turn my camera off.